All right, the next topic that we're going to talk about is partial differentiation. And the reason why is because we want to talk about two really important classes of equations that will be the foundation of how we build our geophysical understanding of how things work. So partial derivatives are derivatives that you take when you have a function that depends on more than one independent variable, independent coordinate. So it could be x and y and z, or it could be x and time, or something like that. The important reason why it's partial is because if you hold one of them fixed, you can vary the other one independently and vice versa. So if you think of a graph where you have the two axes on the graph, you can move in one direction and vary one variable, or move in the other direction and vary the other independent coordinate. And if there's a function mapped on top of both, partial derivatives describe the shape of that function over that two-dimensional space, spanned by one variable in this direction, one variable in this direction. So we can think of surfaces on 2 dimensions, or we can think of fields, like expressions that might go through 3-dimensional space, or even 3-dimensional space and time, things like the evolution of temperature in time in a turbulent 3-dimensional flow is a good example of the reason why we need partial derivatives, is to pay attention to how it's varying in time and in each of the 3 independent directions. And we'll see when we get a little bit farther along into vectors and tensors that it really, our choice of how we set that up depends a little bit. There are lots of different advantages and disadvantages to taking that in different ways. Okay, so we'll have 2 different kinds of equations. An ordinary differential equation, and it's called ordinary because all of the derivatives are with respect to only one variable. So we might have a second derivative with respect to t, or time in this case, of a function of time, a first derivative with respect to time of some other function, but also just of time, and then maybe just other functions of time, and then it's an equation, so you could set that equal to 0. And you can imagine by choosing different f's and g's and h's, you can make this really a generic. This is called a second order ordinary differential equation because the derivative, the highest order is second in this case. But it can also have first derivatives and things without derivatives included inside the second order differential equation. And as we've already talked about, derivatives are linear functions. And so if the f and g and h are also linear functions, then we could say that this was a linear second order ordinary differential equation. If instead f or g or h were nonlinear functions, then this could still be a second order differential equation, but we would say it's a nonlinear differential equation, and you could imagine that we actually multiplied a derivative times some other complicated function that was, and then that would be nonlinear as well, because it would be blending part of the derivative with a function that depends on time as well. Okay, but we can imagine and we can check how these functions are linear in our same old way that we have all along by adding together 2 different inputs and making sure that the function is the sum of the 2 inputs, or multiplying the input by a scalar and making sure that that's equal to the function acting on that input times the scalar on the outside. Okay, partial differential equations is where partial derivatives come in, and partial derivatives, as we said, are derivatives with respect to one coordinate or another, holding the other one, holding whichever one we're not differentiating fixed at the same time. So if we had a function, say g, which depends on both x and t, we could take its derivative with respect to only t, and in this, taking this derivative of this term, we treat x like it's a constant while we're taking the d by dt derivative. And in order to emphasize that, we use the curly d instead of the straight Roman d to emphasize that it's a partial derivative. In a second, we'll talk about how that can be a little bit confusing sometimes. you could have also taken the derivative with respect to x, and in this case you'd hold t fixed while taking the derivative with respect to x. And again, you can build an equation with these kind of derivatives. You could have a second derivative that was second derivative in x. Here I've just written a mixed derivative, which is both a derivative with respect to time and a derivative with respect to x. Doesn't matter which one of those you calculate first, but you hold the other one fixed while you're doing it. And we'll get used to switching the order of derivatives and all those kind of things, which takes a little subtlety sometimes, but in this case it isn't too hard to think about. Okay, and again, if f and g and h and p, those functions were all linear, then this would still be a linear differential equation. But in this case, because we have both derivatives with respect to x and t, it would be a partial differential equation. So it's a linear partial differential equation. And because this one has two derivatives in it, we would say this is a linear second order partial differential equation. One of the times it's maybe helpful to think about the partial derivatives and how they work is when you're thinking about the implications of the chain rule. Let's remind ourselves of how the chain rule works. If you take the derivative of a function y, which depends on x, and suppose the function y depends on an intermediate function u, which is in turn a function of x, then you could write that derivative with respect to d by dy, if y depends only on u, times the derivative of u with respect to x. And so y is a function of u and u is a function of x is what we're thinking about. And so here's an example. What if we take d by dx of the sine of 2 times x, then 2 times x in this case is u. So if we take d by dx of y, which is this piece, the whole sine part, then we still have to go inside to take the derivative of that. So we take first the derivative of y with respect to u, that's sine of u in this case. So that would be cosine of 2x. So we haven't taken any derivatives of the inside yet. We haven't taken any derivatives of the inside yet, but we have taken the derivative of the sine. Now we need to go inside and take the derivative of this, and what comes out of that is an extra factor of 2. It comes from taking the derivative of the u, the inner part, with respect to x. That's this part. And it's just a multiplication of dy du. So first we take this piece based on u, which is the inner part, and then we take u with respect to x as the second part. Okay, so that's nice and easy to think about. But what if instead we take a different function in a different order, where now we think of a function u that might depend on time, that's composed of both a part of it that depends on x, and then x depends on time, and a part that depends on y, and then y also depends on time. So here's an example. What if we take d by dt of sine of t times t plus 2? So in this case, we're thinking of x being equal to the t part and t plus 2 being equal to the y part. So if we take the derivative with respect to time directly and forget about the x's and y's for a moment, then we get the cosine, and then we have to take the derivative of what's inside, which if I did as a product rule, I would get t plus 2 if I take the derivative with respect to the first t, and then if I take the derivative with respect to the second t, I get an extra t. So that's cosine of t times t plus 2 times the whole thing times 2t plus 2. Okay, but what if we think of it instead as the d by dt of x, which x is now a function of t, and y is now a function of t. We have to do 2 steps. We need to first take the derivative of sine with respect to x, and then multiply that by the derivative of x with respect to t. And then the second part is take the derivative of sine with respect to y, and then take the derivative of y with respect to t. And notice that these first two have the curlies on them because they are partial derivatives. We're taking it with respect to x while holding y fixed, and then taking it with respect to y while holding x fixed. So let's see how that goes. First we take the derivative with respect to x of sine of xy times dx dt, and then we take d dy of sine of xy dy dt. That's basically just rewriting this, but for this particular function, we take the derivative with respect to x of this, we get cosine of xy, and then we have to take the derivative of what's inside. That gives us a y out front. Here, remember, we're taking derivatives with respect to x. We still have to multiply by dx dt, which we haven't figured out yet, but that's coming. We do it with respect to y. We get the x out front instead of the y out front, cosine of xy, dy dt. Now, we remember what our x function is and what our y function is to evaluate these two derivatives. We get t plus 2, which is evaluating y, and then we have to multiply by dx dt, but dx dt is just 1, and t, which is evaluating x, and then dy dt, dy dt is just 1 as well, so that gives us a 1, and there we go. That's the same answer that we had here by just taking the derivatives with respect to t directly. This is one way in which you find yourself having partial derivatives. And one thing I will note before we close out this little short video is if you have a y that depends on x or an x that depends on y, you need to be really careful whether you should be using partial derivatives or total derivatives and which one is being asked for, because using a partial derivative implies holding other independent coordinates fixed. And so that takes a lot of practice. We're going to get a lot over the next few weeks.